All right, hello again, everybody. It is Wednesday of week 2. It's actually a beautiful day out for chemistry. All right, before we move into today's new material, I just wanted to reiterate a couple things from past lessons just to make sure that we remember and are thinking about things correctly, okay? So we did enthalpy on Monday, and the biggest takeaway was how to calculate the change in enthalpy for different processes. And so I just need you to remember that whenever we say change in enthalpy, we are actually just saying what? Good, we're just saying heat, okay? Change in enthalpy. So, quick review. Our change in enthalpy. For any process that we're doing, usually change in enthalpy is just kind of a fancy way of saying heat when we apply it to chemical reactions. But change in enthalpy is just heat, Q. Okay, so keep that in mind. It is no different for our purposes in this class. Okay, the second thing I wanted to do really quickly, just to make sure you actually understand how we're applying this enthalpy to chemical reactions, just think about this simple reaction. If we have, let's say, 2NO plus O2 goes to 2NO2. Okay, if we just have that really simple synthesis reaction, and we know that the delta H for this reaction happens to be, we'll say 60, positive 60 kilojoules. What I should be able to do, or what I should be able to ask you, are questions like this. If I react exactly 1 mole of oxygen gas, how much heat is required? And you would look at this reaction and say 1 mole of oxygen gas. Well, there's already 1 mole of oxygen in this reaction, and that corresponds to 60 kilojoules of heat. So it would be 60 kilojoules. But what if I wanted to react 2 moles of O2? What would you do to the change in enthalpy? This is a 1. We're going to make it a 2 because we want 2 moles of oxygen to react. Whatever you do, whatever manipulation you do to your reactant or product, you do the same thing to your change in enthalpy. So since we want to react double the amount of oxygen, you would require double the amount of heat. Okay? Let's say we wanted to produce only 1 mole of NO2. Well, this 60 kilojoules is with respect to 2 moles of NO2. If we only want half of that, 1 mole, you would only require half the amount of energy. Okay, so keep that in mind, that you can manipulate your chemical reaction, and you would do the same exact manipulation for your delta H, your change in enthalpy. Okay? All right, so new material. We are going to be studying a new law called Hess's law. Okay, Hess's law, named after, you guessed it, an old dead white guy. And Hess's law, get a different marker, says that the delta H of a reaction is only dependent on 2 things, okay? The delta H for the overall chemical reaction is only dependent on 2 things. One of them is the enthalpy of the products. The other, can you guess what the other one is? reliant on or dependent upon the enthalpy of the products and the enthalpy of the reactants. Those are the only two things that the delta H of a reaction is dependent upon. What it's not dependent upon is what happens in the middle between the reactants, which you start with, and the products, which you finish with. Okay? So put in another way, if we were to graph enthalpy, so I'll put H on our y-axis, and then just plot here the reaction progress along the x-axis. Let's say our enthalpy for our reactants is somewhere around there. I'm just arbitrarily choosing an amount of enthalpy for our reactants. And then let's say our product's enthalpy is somewhere up here. Okay, that will be our enthalpy of our products. Now, first, you should be able to look at a graph like this, just looking at where the reactant's enthalpy is and the product's enthalpy, and tell me right away what the sign of delta H would be. Okay, can you look at that? Reactants are lower than products, therefore the delta H sign would be positive. Okay, that corresponds to what type of process? Would that be an endothermic or an exothermic process? Good, it's endothermic, okay, because the overall enthalpy went up over the course of the reaction. But what Hess's law tells us is that this delta H of the reaction is only dependent upon where you start with the reactants and where you end with the products. It does not matter how we get there in between. It could go up, down, in between, whatever. It doesn't matter how you get from the start to the finish. It just matters what the start and finish are. Okay? This middle does not matter for us. Okay? So that's what Hess's law is going to tell us. Now, when we start doing problems for Hess's law, it's not going to seem very important, really, of a concept. So what I want to do is just take a minute to kind of go over some fundamental concepts that are used in Hess's law that are actually very important for chemistry as a whole. Okay. Okay, so some fundamental chemistry concepts that will kind of go along with Hess's law that makes it worthwhile studying for us. Okay, so the first thing is that all chemical reactions can be manipulated. Okay, and we just kind of touched on this with the review problem just a minute ago, but I just want to stress that reactions can be manipulated. All right, so let's just think of a very simple reaction. A plus B creates a compound AB, okay? And let's say the delta H for this reaction is 100 kilojoules. Okay, the delta H for that reaction is 100 kilojoules. Now, we can manipulate this reaction in a couple different ways. Okay, the way that we just did it in a review problem was we could just multiply this entire reaction by a number, right? So if we wanted to multiply everything by 2, you could do that. It would just become 2A plus 2B goes to 2AB. Now, we manipulated the chemical reaction. You have to do the same exact manipulation to the delta H for the reaction. Okay, so the change in enthalpy will not be 100 kilojoules anymore because we doubled this reaction, so now it'll be 200 kilojoules. So that's one manipulation. You can multiply by any number. Okay, I chose 2, but you can multiply by 3, 4, 5, 6, it doesn't matter. You can always multiply by any number. Okay, you can also, let's say if we don't want to produce an entire mole of AB, we only need a fraction of that. Let's say we only need a fifth of a mole of AB. So you could divide any reaction by any number. So if we divide this reaction by 5, you would now have 1/5 A plus 1/5 B to produce 1/5 AB. Now again, since we manipulated that overall reaction, we have to do the same manipulation to the delta H value. It was 100 kilojoules, but now we are dividing that by 5, so it would just become 20 kilojoules. Okay, so multiplication, division, those are the 2 manipulations you can do, and there's one more that will be very helpful. Any reaction that's written, you can just simply flip that reaction to create the reverse reaction. Here we had A plus B going to AB. That would be just a simple synthesis reaction, right? Well, what about if you start with AB and you want to decompose it? So we could do that as well. If we have AB and decompose it into its elements, A plus B, that would be known as just flipping the reaction. If you flip the reaction, you have any guess what's going to happen to that delta H value? Good. The sign is going to flip. It was 100 kilojoules for the synthesis reaction. If we flip it and make it a decomposition, it is going to simply become negative 100 kilojoules. Okay? So that's one thing. Reactions can be manipulated. Number 2. Number 2 is that many reactions occur in multiple steps. Okay, many reactions occur in multiple steps. Now think about this. We have a very simple chemical reaction, right? It's a generic one, but A plus B goes to AB. Now that seems simple, right? A comes into contact with B, they combine and make a new compound. But chemistry, of course, is not always that simple. So an overall reaction that looks like this might occur in multiple steps. Let's say first, our first step is that A actually has to react with another element, C. They create AC. Then that AC, reacts with another element. Let's just say it reacts with D to create ACD, another compound. And then finally, we have our ACD then reacting with our B. Let's just say B kicks off C and D from that compound and replaces it. And we finally get our product AB. Okay? Here are 3 steps that this seemingly simple reaction had to go through just to create its AB product. Okay? These are just the steps of the reaction, and if you notice, we can add them up. Okay? You can add up all of these steps, so 1 plus 2 plus 3, and just think about it like a regular algebraic equation, okay? If you had just a regular equation in Algebra 2 in, 9th grade, 8th grade, if you had, let's say, y plus x equals x plus 4, and I said simplify that, hopefully you would think, well, there's an x on the left, an x on the right, So they're going to cancel each other out, and we're going to be left with y equals 4, right? You can do the same exact thing with chemical reactions, with the steps in this chemical reaction. So anything that's on the left side of the arrow that is the exact same as something on the right side of an arrow in one of the other steps, they will cancel each other out. So if you look at this, can you figure out what's going to cancel out? What shows up on both the left and the right side in different steps? Well, I see first here an AC on both the left and the right that can cancel. I also see an ACD on both the left and the right. I see a C and I see a B, or sorry, not a B, a D on both the left and the right. So all that we're left with is our overall reaction. We have A and B on the left, that's leftover, and our AB on the right side, that's also leftover. Okay, so you can do this where you add up multiple steps of a reaction to get your overall reaction that you desire. Okay, so reactions happen in multiple steps. And then the last thing, and I'll just put it down here for number 3, hopefully you can see that. So each of these, if you would think about each of these is kind of its own chemical reaction, right? So each of these steps, I'll just say that's step 1, step 2, and step 3. Each of these steps is going to have their own change in enthalpy, right? So the change in enthalpy of this first step I'll call delta H with a little 1. Then the delta H for the second reaction I'll call delta H with a little 2. And then the third one, delta H3. And now the last thing that you have to remember or know before we start Hess's law is that if you want the delta H for this overall reaction, it is just going to be equal to the sum of all of the steps for your reaction. Okay, so here we had our 3 steps. If we add up the delta H values for each of those steps, we would end up getting our delta H for the overall reaction. Okay, so keep that in mind. 1, reactions can be manipulated. We're going to have to do that a lot in Hess's law. Number 2, reactions occur in multiple steps. You can add up those multiple steps to get your overall reaction. And number 3, the delta H for the overall reaction is just equal to the sum of the delta H's for the steps. Okay. The presenting sponsor for this chemistry lecture is hand soap. Wash your damn hands!